start recording here. Okay, so to begin with, what we're going to do here briefly is review questions as succinctly as possible from chapter 7. Okay, this is, as you can see, chapter 7, question number 26. So converting liquid water to solid water releases this amount of energy. Okay, that's an enthalpy, a heat that's being released. And then it wants to know what is the sign for this process, right? The reaction showing heat as a product or reactant. How many kilojoules are released by freezing that amount of water? How many kilojoules are released from that? And how many kilojoules are released from that? Okay. So the basic concept here are phase changes. All right. The general idea of what's occurring is, what happens is, if you were to look at temperature and the addition of heat in the form of enthalpy, as you add it to, so this is temperature, as you add it to matter, there's going to be a region where there's going to be a phase change. So if we call this the solid region, and this right here would be the phase change from solid to liquid, and then here would be when it's a liquid, and then this right here, actually, you know what we actually need to do is not temperature and enthalpy. I have those reversed, my apologies. What it needs to be is enthalpy here and temperature here. So the temperature is going to depend generally on the input of heat. Okay, your independent variable is enthalpy. The dependent variable is the temperature. Does that make sense? So the temperature is going to depend on the input of energy or removal of energy. You guys follow that idea? Kind of like when you turn on the heater, the room gets warmer because you're actually adding heat to the room. You turn on the AC, you're actually removing heat from the room. That makes sense? Okay. So this is going to be the phase change from liquid to gas right there. And then finally, we're going to have the gas phase. We can call this the solid phase region, whatever you want to call it. This is the liquid phase, and this is the gas phase. So as you add heat, you're going to increase the temperature of whatever you're talking about. Say it's ice. The temperature of the ice is going to increase until it reaches a certain point. That point, the temperature right there, where it stops changing, as far as the temperature goes, the temperature will actually stop changing, and it'll kind of become a flat line. And that's when it's going from solid to liquid. So we call this melting, if you will, going that direction. And if you go this direction, it is solidifying. But this temperature right here, where there's no temperature change, we call that either the melting point, or you could call it the temperature of fusion. Fusion is where it goes from a liquid to a solid. It's the opposite of melting. Melting is going from solid to liquid. Fusion is going from liquid to solid. Okay? There's no temperature change at that time when you are going through a phase change from solid to liquid or liquid to solid. There is no change in temperature because all the heat is going into forcing that literal change in phase. All the heat that you add is going into the change in phase. It is actually breaking the bonds that then transform it from a solid to a liquid. Does that make sense at all? So you'll actually see it flat. Okay. That's why if you make pure ice water that contains no ions, a mixture of water and ice in a cup, it'll literally be at 0 degrees Celsius. Okay, that cup of ice water is at 0 degrees Celsius. Now the ice will be at a different temperature, but the ice water itself will be at 0 degrees Celsius because it's a phase where there is melting and fusion going on. Okay. Now, once all of that ice has melted, you're now at a liquid, and you start adding more heat, the temperature starts changing again until you hit another point right here. And this point right here, coming across, will be another temperature point. This point right here, this will be called you could call it the evaporation point. You could call it the temperature of evaporation. It's the point at which you actually literally reach where it's, well, another name that you guys would recognize better is the boiling point. Shouldn't really call it evaporation. That's different. Boiling point is the correct term. Okay, you've heard of the boiling point. You know, you put water in a kettle and you start it heating up. It starts to bubble and you see it boiling. Boiling, that boiling temperature, once you hit that boiling temperature, the temperature of that water that's boiling cannot go higher either. If you put the thermometer directly into just the water, not touching the metal, because the metal can get hotter, but just the water will be at exactly 100 degrees Celsius and will stay at 100 degrees Celsius. It cannot go higher than that. Okay. So for water, when you hit a boiling point where you're going from liquid to gas, okay, that is the boiling point. And then at the phase, and then above that, you enter into the gas phase. Does this make sense, guys? Okay. Phase changes should be, I hope, fairly accessible. There's something you've experienced in real life and should be more familiar to you than looking at atoms. This is something familiar. Okay. Now, I wanted to review this just as briefly as possible because now, if we go back to the previous page, what is the sign for delta H of this process? The process is converting liquid water to solid ice. Okay, so 26A says converting liquid H2O to solid ice. What that'll mean is you're going from H2O, liquid is another way of representing it, to H2O solid. You can essentially kind of create a reaction of this. It's not a chemical reaction. This is a phase change. It's a physical process. Okay. This is a phase change, which is a physical change. It is not a chemical change. Okay. But you can write this as a change. You can write an equation for this nonetheless. Okay. This is freezing or fusion. Now, it says, they do say to you, energy is released. That is one of the other terms that they do use in that first part. Does that mean that energy is absorbed by the water or goes out into the rest of the universe? Goes out to the rest of the universe because it's released. Does that make sense? So therefore, is it a reactant? And I put this in quotation marks, reactant in quotation marks, because this is not a chemical reaction. I guess you could call it a physical reaction. Is it a reactant or a quote unquote reactant or a quote unquote product? Pardon? It should go on this side here. It's going to be a product because it's released. Okay. So it becomes plus 6.02 kilojoules per mole. Okay. You guys with me so far? Any questions about that? Is that clear? Any concerns? Okay. If there aren't any concerns, then let's look at that question one more time real quickly. What is the sign for the process? Okay. We've written a reaction showing the heat as a product or reactant. Now, What is the sign of delta H fusion? Positive or negative? It is negative because energy is released. Okay. For enthalpy, when enthalpy is released, the release of enthalpy from the system to the surroundings is a negative value. So it's negative 6.02 kilojoules per mole. Now, I'm not going to try to confuse you guys, but it is important that you understand that fusion and melting are opposite and equal. Going this direction is fusion. Going this direction is melting. Okay? So what that means is the delta H of melting is equal to a positive 6.02 kilojoules per mole. The opposite process is an equal value with an opposite sign. Okay? The same value, but just with a flipped sign. Okay? If the process is opposite, that means the value, the actual magnitude is the same. The magnitude is the same. The only difference is the sign. Okay? Does that make sense? Okay. Any questions about that? It's like whether you add money to your bank account or remove money from your bank account. You remove money from your bank account, it shows a negative value. If I remove $1 from my bank account, it's minus $1. If I add $1 to my bank account, it's plus $1. Same thing here. Okay? Any questions? Okay, I'm going to move on to the next part. How many kilojoules are released by freezing 2.5 moles of water? Okay, so you know what? I'm going to kind of skip B and go to C because C is going to be essentially the same thing as B, but a little more complicated. The calculation for C and B are almost identical. The process is almost identical. There's just an additional step for part C. Okay, so I'm going to go to part C now. 26C. What is it? It is 32 grams. So if we've got 32.0 grams of water, and we know that this is freezing 32 grams, and the delta H of freezing is equal to minus 6.02 kilojoules per mole of H2O. We know that that means we need moles of water. Okay, any questions so far? Okay, so I'm going to put minus 6.02 kilojoules over 1 mole of H2O. And now I can see that grams and moles are not going to cancel. So I need a way to get moles of water. Does that make sense? So what additional thing do I need to stick in the parentheses here? Something to convert grams to moles. How do I do that? What's the thing I need? This is chapter 6 material. Converting grams to moles is chapter 6. Part of the lab you guys just turned in. Not kcal. Talking now about calories, which is just another unit of energy like joules. I want to go from grams to moles. I need the molar mass. To do this, we need the molar mass. Okay? How do we get that? Periodic table. The molar mass of H2O is going to be 2 times 1.008 plus 1 times 16. That is going to end up at basically 18.016 grams of H2O per mole of H2O. Is everyone comfortable with where I got that from? Everyone okay with that? Okay. So then I put 1 mole of H2O on top because I need moles of H2O to cancel. And then I put 18.016 grams of H2O on the bottom to get grams to cancel. Plug this into my calculator, and I got my answer. Okay. Now, the only difference between part B and part C is for part B, in part B, you don't need the molar mass because you're already given moles. Okay. In part B, you would just plug in a quantity of moles here, multiply it by this, and you'd be done with part B. Okay? Questions about that? Okay? Am I moving too fast for anyone? Okay. Last question then, part D. How many kilojoules are absorbed by melting 1 mole of ice? Part D, 26D. Literally, how many kilojoules absorbed when 1 mole of H2O is melted? Now, do you guys understand how to do that? So remember, our delta H of melting is equal but opposite of the delta H of freezing or fusion. They are equal but opposite. That's why the negative sign's there. They are equal but opposite. Okay? Which means this is equal now to negative 6.02 kilojoules per mole, which means the final value we'd be using here is 6.02 kilojoules per mole. That makes sense? Okay. So now it's just 1 mole of H2O multiplied by 6.02 kilojoules per 1 mole of H2O. And we've got the very surprising value of 6.02 kilojoules. Okay? Questions? Any concerns? Because we're using melting, so it needs to be a positive value. If we're using melting, it needs to be a positive value. The key here is what I did was I said the delta H of melting is opposite the value of freezing, which is a negative of the negative, and therefore a positive value. Does that make sense? Negative times a negative. This is the only time in life when two wrongs make a right. The only time 2 wrongs make a right is when you multiply 2 negative things. It doesn't work in life, of course. You know, commit 2 crimes doesn't suddenly make the law happy with you. But multiply 2 negative values, you end up with a positive. Okay, you guys good with that? Okay. Another way to remember this is they do say in the question how many kilojoules are absorbed, which means the answer needs to be positive. You can't have negative values of moles, because moles are literal matter. You can't have negative quantity of water. If someone offers you a cup and says, here's negative 5 liters of H2O, I don't even know what that is. You can't get less than 0 H2O. right? Good with that? Awesome. Okay, so that is 26. Any questions about that, guys? Okay, then we're going to jump to 29. Glucose, also known as blood sugar, when measured in blood, has the same formula as every hexose, which is C6H12O6. Now, we're asked to write the equation for the combustion of glucose with oxygen to give CO2 and H2O. Does anyone need me to? So let's see, we said 29C. Okay, so you guys good with the idea of how to do 29A, right? A? Sure. Okay, so not with a laser pointer. Let's try with an actual pen. So 29A tells us that one of our reactants is glucose, C6H12O6. They tell us that it is a combustion reaction. So even if they hadn't told you O2, combustion requires that it is reacted with oxygen, diatomic oxygen, O2. But they did tell you, write the equation of combustion of glucose with O2, right? To give, which means there's the arrow. When it says to give, there's your arrow linguistically. To give means it's now producing carbon dioxide, which means carbon dioxide and water. When it's with, that's a plus sign, glucose plus O2. To give is your arrow, and then CO2 and H2O means CO2 plus H2O. That makes sense so far? Okay, awesome. So now I just write that CO2 plus H2O. You guys good with how to balance this one? Okay, if I just do it quickly, or do you guys need a little bit more? You guys doing okay on balancing? Okay. 6 carbons and 6 in front of the water gives me 6 carbons, CHO. So we started with, find 6, 1, 12, 2, and finally we had 8 here and 3 on that side. So we first added a 6 there, gives us 6 here. Putting the 6 there now means we've got 12 plus 1 is 13 oxygens. Okay, now we went 12 and we put a 6 in front of the H2O, which now gives us here, changes this to a 12 and now changes this to 18. We've got 18 oxygens. We've got an 8 here. If we just go 6 plus, if we put a 6 here now, we've got 12 plus 6, which gives us 18 total. And you can see that it is now balanced. So that's our balanced equation. Okay. Next, part B of 3.8 kilocal is released by combustion of each gram of glucose. How many kilojoules are released by the combustion of 1.50 moles of glucose? Okay, so we're told in part B, I think it's for every gram of C6H12O6, we release 16 kilojoules. I think the question is asking how many kilojoules, so we're just going to use kilojoules. Why make our life difficult? Let's just stick with the kilojoules. 16 kilojoules, which means therefore there's a couple of ways of doing this. We could find a delta H reaction in kilojoules per mole to begin with, because we've got grams and a quantity of kilojoules. We could calculate how many kilojoules per mole. That's doable. Or we can do this whole thing as one problem rather than doing it in multiple parts. You guys want me to just do it as one thing? Okay, let's do that. So we're looking for then how much energy in kilojoules released from, what is the quantity? The quantity is 1.5 moles. Like so, okay? Now, something else to keep in mind, which side does the enthalpy go on? Is it a product or a reactant? It says energy delta H reaction is released. What does it mean if something's released? It's a product, okay? That means product. So plus delta H reaction also means delta H reaction is negative in sign, just to keep in mind, okay? So how much energy? To answer the question, how much energy? We're going to say delta H is equal to, we're going to start with 16 kilojoules are released per 1 gram of C6H12O6. That's what we're told. 16 kilojoules per 1 gram. Okay? Does that make sense so far? Now I'm going to tell you guys, to save us a little bit of time, the molar mass here, the molar mass we're going to use is 180 grams of C6H12O6 per 1 mole of C6H12O6. That's the molar mass, okay? So our molar mass is this guy here. I know it's getting a little busy. So we need to put 180 grams of C6H12O6 per 1 mole of C6H12O6. And finally, it wants us to do this for 1.5 moles. Okay? So we add 1.50 moles of C6H12O6, like so. Do that calculation, and that will give you your final answer. Okay, so you will take 16 and multiply it by 180, and then by 1.5, and you're done. Any questions about that? Any confusion? Any concerns about where things came from or why I did things? You guys good? Okay, you guys are good. I'm going to move on to, let's see, was there another part? C. What is the minimum amount of energy a plant must absorb to produce 15 grams of glucose? Okay, part C. Minimum amount of energy to produce 15 grams of glucose. This is a great question, and not just because I assigned it. Now, the first part of the reaction, the first part of the question, previously, we talked about combustion, okay? The minimum amount of energy to produce glucose production, also known as the synthesis, of glucose. Does that sound like combustion to you? Does that sound anything like combustion? No, it does not, right? When I say the synthesis or production of glucose, that does not sound like the same thing as the combustion of glucose, right? Does that make sense so far? Okay, so the production of glucose is the opposite of combustion. Is the opposite of combustion. So what that means is the reaction for production is also known as photosynthesis, is going to be the opposite reaction. It's going to be 6 CO2 plus 6 H2O, giving you C6H12O6 plus 6 O2. And it's going to require, what was it? It was, it required 16 kilojoules per gram per 1 gram of C6H12O6. If the enthalpy is 16 kilojoules per 1 gram that's released in combustion, you're going to require per gram a minimum of 16 kilojoules to be absorbed as you synthesize the glucose. Okay? You guys with me so far? Okay. If you guys are with me so far, there's a lot going on here, but the way you do this calculation, for the minimum amount of energy to produce 15 grams, becomes 15 grams times 16 kilojoules per 1 gram of C6H12O6. And 16 times 15 is some sort of big number with a positive sign. Because energy is absorbed. Okay, here, energy is being absorbed here to drive the reaction, to drive the synthesis of glucose. We are investing energy. Light is absorbed by plants to synthesize glucose, to take carbon dioxide and water and build a larger molecule. Okay. Any questions? Okay. Anyone need more information, more explanation? Is there any confusion on question 29? Okay, if not, let's go to the next question. There we go. Use your answer from problem 7.54 to calculate the following. Well, we should probably be looking at question 7.54 then. Hold on a second here. Okay, so here is question 54 for the reaction. CO2 plus O2 giving you, carbon monoxide plus oxygen giving you carbon dioxide. There are the equilibrium concentrations. So write the equilibrium expression for the reaction. What is the K at this temperature? Are the reactants or products favored? So the equilibrium expression. So to begin with, how comfortable are you guys with the concept of equilibrium? You guys good on equilibrium? No? Confused? Okay, let's see if I can do this super fast. How comfortable are you guys with the general idea of the rate of a reaction? You guys okay at all with the idea of the rate of a reaction? The velocity of a reaction. You guys okay with that at all? The general idea of molecules moving through and processing. All right, let's see if I can do this really, really fast. So reaction A going to be, this is endothermic versus exothermic, but it doesn't matter about endothermic versus exothermic. We'll just look at an exothermic reaction. So talking about a spontaneous exothermic reaction where the energy of the bonds in A are higher than the energy of the bonds in B. So it's a downhill process, okay? You've got A being converted to B plus delta H. Here, energy is released. It's exothermic. You guys okay with that? Good on that. Okay. The general idea would be looking at delta H on this graph here. We'll just say that this is time. Then if you put the energy of A there, the energy of B here, the general process always takes on a form of a graph like this, where you have a super high point there. This is called the transition state. The transition state is the highest energy point in a reaction during the chemical process, okay? Imagine the general, I mean, if anything, the easiest way to imagine this is as you are trying to put energy into breaking a pencil, you'll feel a point at which it almost breaks and then it snaps, right? That makes sense? There's a point right between where it snaps, where you can almost feel it break. That makes sense? That's the transition point between when the pencil is whole and when the pencil is broken. All right, and this is a good point for me to actually use my video. So if we're talking about a pencil, okay, as a chemical reaction, the energy between when the pencil is whole and when it actually breaks, when I'm flexing on it, but it is not quite broken, that point right between when it breaks and is not broken, that is the transition point between whole pencil and broken pencil. Okay, when it's almost broken, but not quite. And that is also the highest amount of energy because it's going to be that point at where I've put the most amount of effort into break. That makes sense? You can feel your arms go tighter and tighter and tighter when you're trying to break something. And it's just right before it breaks that you've put the most amount of effort into break. That makes sense? You put the most amount of effort into breaking that pencil right before it snaps. That's that highest energy point. Okay. That highest energy point is what we call the transition point because it's the transition point between the two states, between the state of being whole and between being broken for this pencil that we're talking about. Okay. So if that makes sense, then the transition state is that highest point between the two product versus reactant, whole pencil and broken pencil. Okay. Now, every time a pencil is snapped, it has to reach that highest point before it breaks. It requires the effort to get to that highest transition point. You have to get to that highest point right between that, and then it'll become a broken pencil. That makes sense? Okay. So the rate of, in this case, my example, breaking pencils is limited by how quickly the highest energy point, the transition state, can be reached. Okay, you're limited by how you can reach that highest energy point. That makes sense. Okay, so you're limited by whether or not you can reach that highest energy point. You know what? I'm okay with the fact if we spend most of the time tonight talking about chapter 7, you guys will do some practice on chapter 6. I think you can handle it. I'm confident in your abilities to handle it. It's good review, but it's good for me to also review this. Okay, you guys okay with that idea? Okay, so transition state is that highest energy point in breaking pencils. Okay. The rate of the reaction is limited by climbing that hill up to that highest energy point. Okay. If it takes a lot of effort to break pencils, it's going to take me a lot more time to break a lot of pencils. That should make sense to you. If it doesn't, if pencils are really weak and they snap very, very easily, I'm going to break a whole lot of pencils very quickly. You can just imagine that, right? You can imagine doing that yourselves. Is it easier to break pencils when they're super thin or when they're super thick? It's always going to be easier to break a thinner pencil. It's going to take less effort, right? They might even almost break on their own. If there's not much energy required, they're going to snap almost on their own. Okay, that makes sense to you guys? That's the idea of what we call the activation energy. So the activation energy is equal to the energy required to go from, say, reactant to transition state, or from, well, yeah, we'll just say from reactant to transition state. That's what we're going to go with. Okay. It's the amount of energy required to go from reactant to transition state. So the energy difference between here and here on this graph, that right there is our activation energy. Okay. The amount of energy required to reach the transition state. It activates the reaction. Okay. It snaps the pencil. That makes sense? Okay. Any questions so far? Okay. If that makes sense, then let's see here. In order to be able to finish this explanation, good so far. You guys with me on activation energy, transition state? Okay. Now, if that makes sense, then we understand that the rate of reaction depends on the size of activation energy. Okay. The larger the activation energy, the slower the reaction. The smaller the activation energy, the faster the reaction. Okay. Because it's going to take more effort each pencil you try to snap if it requires more energy to snap that pencil, right? And if it requires more energy to snap that pencil, you're going to be slower at snapping pencils. Okay. I know I've never used that analogy before, but I like it. I probably use it again. It makes a lot of sense. It's a very visceral, real image that you guys can think about. It's very accessible. So we're good so far then. Let's talk about reversible reactions. Are you guys comfortable with the concept of reversible reaction? A general idea of reversible versus irreversible. So some reactions are reversible. Others are irreversible. Okay. Irreversible reactions are ones that you cannot undo. Okay. You cannot undo some things. There's some things you cannot undo. Much as we'd like to have the ability to rewind time, you can't do it. Some things can be reversed as a process goes. Other things just simply cannot be. Some reactions are irreversible. For example, in general, the combustion of paper is irreversible. Okay. Now, you could argue if I gathered up all of the molecules of everything that was used, I could recombine them into something that was burned. But you can't recreate a piece of paper after you burn it. Even if you were to create some sort of piece of paper, it wouldn't have anything you'd written on it. Okay. Even if you were able to take all of the molecules that were burned and produced from the burning of it and put it back into the piece of paper, you would not be able to recreate whatever had been written or printed on that piece of paper. That makes sense? Okay. You guys good with that so far? Okay, so irreversible reactions do exist. These are things that cannot be undone. Okay, some reactions can be undone. Some reactions can be undone. That's why you have rechargeable batteries. That's why your phone can be charged. The chemical reaction in your batteries is reversible. That's why they are rechargeable, because those are chemical reactions happening. Okay? And the only reason they're rechargeable is because they are reversible. Good so far? Okay. Any questions about this? So yeah, all of this is in the study guide. All of this is on the Canvas site. So a reversible reaction is one that can go in either direction, from products to reactants or reactants to products. Okay. The example of this could be something as simple as if you did silver nitrate plus something like sodium chloride. Now this will produce, no, let's not do that reaction. That's, well, fine. We'll say that this reaction is reversible. Okay, you'll get from this reaction silver chloride that is solid plus sodium nitrate that's going to stay aqueous in solution. Okay. Theoretically, this reaction is reversible. You can, if you were to add enough energy, get this stuff to go back in the solution. Theoretically. Okay, this is, we're going to say that if there's energy released here, which is true. Okay. If this is a reversible process, then you've got a forward reaction and a reverse reaction. Okay. A reversible reaction is going to have a forward reaction, and then just like the idea of turning on a videotape and rewinding it, or watching a video on YouTube in reverse, the whole process goes backwards. Okay, and that is the reverse reaction. Okay, so you could actually break this down into two separate reactions. The forward reaction is going to be the silver nitrate plus sodium chloride, giving you silver chloride plus sodium nitrate. And then the reverse is going to be silver chloride plus sodium nitrate, giving you silver nitrate plus sodium chloride. Okay. All I've done is write these as both going forward, but they are just simply opposites of each other. Okay. This is our forward reaction here, going in that direction. And you can see, if you look carefully, that this process here is just the reverse direction of this one. We're going the opposite direction. We're going silver chloride plus sodium nitrate, becoming the reactants of the original reaction. Make sense so far? So forward and reverse. Okay. Now, for reversible reactions, as soon as the forward reaction starts, the reverse reaction begins as well. But they will be going at different speeds. They'll be going at very different speeds. Okay. If you start the forward reaction, they have to be going at opposite speeds, because to begin with, there's not going to be very much of the product to reverse back into the reactant initially. Okay. Anyone need more time with this slide? Okay. So let me show you some numbers. If we talk silver nitrate, and we do a table of like time, and we just look at, say, moles of silver nitrate, moles of sodium chloride, moles of silver chloride, and moles of sodium nitrate, then we'll say time at time 0. Let's say there's 10 of these, 10 of these, and at time 0, we're going to start with 0 and 0. Okay. Then at the first time we look, maybe there'll be 9 and 9, and then there's 1 and 1. Okay. And then there's going to be, because it's going to be still at time 2, it's still going to be going faster forward. Maybe this is in seconds, 0, 2, 2, 3 seconds, 4 seconds, 5 seconds, 6 seconds. Okay, so between 9, you know what, in seconds, let's even do this even faster. Okay, let's just say that this reaction starts out really fast. So at first, you're going to see it drop to like something like 5 and 5 and 5 and 5. That's even that is bad. That's not going to give you the real idea, because the problem is okay, we'll stick with 5, 5, 5, and 5. Now, the forward reaction is going to slow down. So suddenly it's going to go 3 and 3, and then maybe you get 7 and 7. Okay, it's going to slow down to something like 2.8, 2.8, and here you're going to get something like 7.2, 7.2. It's not going to stop though. This could start to go 2.9, sorry, 2.7 is what that was supposed to be, 2.6, 2.7, 2.6. But these concentrations at some point are going to actually stop changing. Okay, you won't see a change in concentration. This will be 7.3, 7.3, 7.4, 7.4. Now, if you were to look at these numbers, you'd say the reaction has stopped. But that's not actually true. Okay, what's actually happened is you can't measure a change in the values. But what's actually happened is the rates have become the same. The rates are the same. So as soon as A is converted to B, B is converted back to A, and there's no change in the value. And this gets a little bit tricky to think about, but you can imagine two jugglers at this point, okay? And they start tossing some balls back and forth, two jugglers, okay? The first juggler, when he first tosses the first ball, the other juggler is not going to have any balls to throw back. That makes sense? Okay. But as soon as the other juggler starts catching the ball, and then another one, he starts tossing them back. And with time, it reaches an equilibrium where as soon as a ball is thrown by one juggler, another one is thrown by the other one. And you'll see that if they were to reach an equilibrium, the rates at which they're tossing, it would look like just as one is being caught, they're throwing another one. Catch and throw, catch and throw. Okay. And so it won't look like either juggler is moving faster than the other, and the number of balls that the juggler is in contact with at any time will be the same number. Okay. So if you were to talk about the quantity of objects that the juggler is holding, it'll be the same number, one or the other. Okay. But if you were to look at the actual process, you'll still see the objects flying through the air. That makes sense? The objects will still be flying through the air, but they'll be in contact with the same number of objects. And in that same fashion, number of products and number of reactants doesn't change, but the reactions are still moving forward and backward, simply at the same rate. That makes sense? Okay. So for reversible reactions, when the rate forward is equal to the rate reverse, there is no what we call net or total change in quantities of product or reactant. This state, this is a condition, a state, is called equilibrium. Not scribble out over equilibrium. It's called equilibrium. Okay. Equilibrium is when there is no change in the quantity of product or reactant, even though the reactions are still both occurring. So both forward and reverse reactions are still occurring, but at equal rates. Okay. This is also called a dynamic equilibrium. A dynamic equilibrium because things are moving. It's dynamic because things are still moving, but it's an equilibrium because there's no change in the quantities of product. There's no change in the quantities of reactant. That makes sense. You guys with me so far? Okay, if you're with me so far, you guys okay if I move forward? Are there any questions about equilibrium, rates of reaction, anything I've just gone over really briefly? Any questions? Okay. So then for a reaction at equilibrium, you can write an equilibrium expression. Now, the problem with the book is it does something really weird here. It completely ignores the fact that we don't talk about concentration until a different chapter and says, oh, concentration, I think. Look at your book. Equilibrium equations. There it is. Equilibrium concentrations. It says concentrations without introducing the concept of concentration. Okay. It's kind of problematic because you guys don't, this is a concept that you guys haven't learned yet. And it goes, we're going to use it, but not tell you what it is. It'd be like giving someone keys to a car and saying, we're not going to teach you how to use it, but go ahead and drive. It'll be fine. Well, we're going to do that, okay? And what they do is, the concentration is an amount of substance per unit volume of, I should say, substance in a mixture per unit volume of total mixture. Okay. This is a little complicated because what this means is, remember what we're talking about, homogeneous mixtures. Now, that's a concept we haven't talked about since chapter 1. Okay. Homogeneous mixtures are a concept from chapter 1. Homogeneous mixtures means a mixing of more than one substance. So it's no longer a pure substance. It is a combination of substances. It's a mixture of substances. And we're no longer talking pure substances. We're talking mixture. We've taken carbon dioxide, nitrogen gas, oxygen gas, put them into a tank. They don't react. There's no chemical reaction. And they're all just hanging out with each other, like the air you're breathing. The air you're breathing is a homogeneous mixture of gases. Okay. Homogeneous mixture means it's all equally spaced throughout the entire volume too. Doesn't mean that it's not like those mud and water where things separate out. This is a homogeneous mixture where everything mixes equally and it's all intermixed. Okay. So that means that you were going, so for concentration now, we're talking about a quantity of one substance, usually in moles. There are other units of, there's other ways of measuring concentration, but it's going to be typically in quantity of substance in moles over volume in liters. And this has a specific thing. This is called molarity, which is a type of concentration. Okay. Now, I know there's a lot of concepts here, and it's one of the few things that I disagree with how the book is organized. Okay. Throwing this at you without really throwing it at you. So we're not going to do a lot of calculations with molarity. Instead, what we're going to do is just talk about concentration and give you the values of concentration, not ask you to calculate concentration, give you the values of concentration for this chapter. Okay. You guys okay with this? Okay. Now, if that makes sense, then let's finish this out and then we'll look at the problem. Okay. So the equilibrium expression is a way of calculating an actual value from concentrations of product and reactant systematically, so we have something we can actually quantify. Okay, this is a systematic quantification system. God, that was a bad word. This is a systematic way of quantifying equilibrium. Okay, it's a way of being able to compare equilibriums, because not all equilibriums are created the same. Just because you've reached equilibrium doesn't mean all of your reactant was converted mostly into product, and so most of your product is now product. You could end up with a state where it is 50-50. You could end up with a state where it's 75-30. 75-25, to be accurate, if we're talking 100%, okay? You can end up with equilibriums occurring where not very much product was created before you reached equilibrium. All right. So how do we do this? For the reaction, A with a coefficient lowercase a. You know what? Let's actually use a real reaction. For the reaction, C6H12O6. This is a bad idea. We're not going to use that reaction either. Combustion's not reversible. I don't have any examples in my study guide, of course. Ah, there we go. For the reaction, CO plus 2H in equilibrium with CH3OH. The equilibrium constant, or equilibrium which is a capital K, is calculated from the equilibrium expression, which is, in general, products over reactants, but done in this fashion. The product concentration represented with brackets, CH3OH, over concentration of 2 carbon monoxide and concentration of H2. Now the problem is the coefficients have an effect here. So you actually put the coefficients as superscripts. Technically we could put a 1 there and a 1 there, okay? And imagine a coefficient of 1 here and a coefficient of 1 here, like so. Okay. That's an example of how to write an equilibrium expression from a reaction. You guys okay if I move forward? Okay. So I'll do a symbolic representation of that now. If you have the reactants A with coefficient A, so these are the coefficients A, lowercase letters will be coefficients, capital letters represent the symbolic chemicals. We put them in equilibrium with, also a bad idea. Let's do them in equilibrium with D plus E, because a capital letter C and lowercase c are really ugly to try to use as symbolic representations. So I like to use D and E. Then the equilibrium expression, the constant can be calculated from concentration of D raised to the power of the coefficient D, concentration of E raised to the power of E, coefficient, over concentration of A to its coefficient, B to its coefficient, okay? And if you use that formula from that reaction, you'll always get the expression correct, okay? Does that make sense, guys? Okay. Good so far. You guys with me so far? Okay. Now that's the equilibrium expression, okay? So let's look at the problem now. For the reaction, CO2 plus O2 giving us CO plus O2 giving us CO2. And here are your equilibrium concentrations. Write the equilibrium expression for the reaction. So part A, we can now do, you can see that K is equal to concentration of CO2 squared over concentration of CO squared plus concentration of O2, like so. Or not plus, sorry, that's a multiplication. Do not do addition. That is multiplication, like so. We do addition there, that's really bad, okay? It's multiplication. Good so far? Okay, so this is our products, that's our reactants, coefficients are superscripts, and we're done. Okay, questions? Now, to get the value of K, you just plug in the concentrations you're given. This is just literally plug in the numbers that are sitting right here. So plug in 0.11 mole per liter squared and so on and so forth, okay? You guys know how to plug in numbers into equations. Plug it into your calculator, you're good to go. Okay, you end up with, yeah, 0.015 mole per liter there, squared. No, not squared. We're not going to do that, okay? So you guys know how to plug these things in to this thing and come up with the answer that you're supposed to have, okay? Good with that? Comfortable with that? So that's question 54. Now looking at question 56. At equilibrium, when CO2 is equal to blah, 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 just plug it into the expression you already have now. So 56 is literally plug it into that expression we've got. All you have to do for 56 is take K is equal to concentration CO2 squared over concentration CO squared concentration O2, and plug in these things, and you've got A and B done already. The hardest part of 56 is actually 54. That makes sense? Any questions about 54 or 56? Guys, okay? All right. Concerns, questions? That's 56. Done. Okay. 60. I think that could be, we're getting close here. Okay, so 60. Hydrogen chloride can be made around the reaction of chlorine and hydrogen. So there's the reaction. For this reaction, there is, so this literally is your K value. There's your K value. You're given the K value, okay? And you know the delta H. Okay. So, looking at this information, delta H, what's the sign of delta H? It's a negative sign, okay? So what does that tell you? Is this an exothermic or endothermic reaction? It's an exothermic reaction. Negative sign, exothermic reaction. Delta H negative means exothermic, okay? Negative delta H will always mean an exothermic reaction. So, A, tick. Are the reactants or products favored at equilibrium? Well, how do we tell? So part A, this is from the sign of delta H. Part B, how do we figure out part B? Where does this come from? I didn't actually talk about that today. So if it's not jumping out at you, jump back to K, okay? Look at K. What do values of K actually mean? What do they actually mean? They do mean something. There's a lot of information you can get from K. All right. Remember when I said, did most of the reactant, that's really hard to read. What I'm trying to write there is turn into. Turn into product before equilibrium was reached. That's not even a real word. Let's try. Was barely any product made before equilibrium was reached. Are the levels of product and reactant relatively equal at equilibrium? These are all questions answered by the size of K. All right. So no matter what, whether you are looking at K and you have a really complicated K expression, if you have a really complicated expression or you have a really simple one, this can always be said to be approximately equal to products over reactants, the concentration of the products over the concentration of reactants. It's very, very roughly equal to the concentration of products over the concentration of reactants. Does that make sense? Because that's literally what it is. You've got the products on the top, the reactants on the bottom. Okay, it's not perfect because you may have different types, and the exponents can make a difference, but very roughly equal to products over reactants. Does that make sense? Okay, and if that's true, then when K is roughly equal to 1, then there is very roughly equal amounts of product and reactant, roughly, okay? When K is much, much, much larger than 1, there's definitely more product than reactant. If K is 1,000, there's clearly more product there than reactant. Okay, so a whole lot of reactant became product before equilibrium was reached. Okay, a whole lot of product got turned into reactant before equilibrium was reached, because in order to get a value of 1,000, you've got to be doing something like 2,000 divided by 2, or 10,000 divided by 10. Okay, which means quantity of product is much larger than quantity of reactant. Does that make sense? And finally, when K is much smaller than 1, that doesn't mean negative. That just means a decimal value. Okay, smaller than 1 still means positive. There's no such thing as a negative K. But much smaller than 1 means 0.0001. So you're taking something like a value of 1 and dividing it by 1,000. Okay, so when K is much, much smaller than 1, you've got very little product and lots of reactants at equilibrium. So what this tells you is, did very much of the reaction forward occur before equilibrium was reached? Okay, did very much of the reaction occur forward before equilibrium was reached? Does that make sense? Did the reaction almost completely occur before equilibrium was reached? Did the reaction kind of go somewhere in between? So what we're saying is, what do the values of K actually mean? Well, did most of the reactant turn into product at equilibrium? For that, K is much, much, much larger than 1. Was barely any product made before equilibrium was reached? K would be much, much smaller than 1. Is it somewhere in between? K is somewhere close to 1. Okay, that's what we're saying here. It's somewhere between like 1 and 100 probably would be a low K. When K is much smaller than 1, we're talking about something like on the order of 0.001 and smaller. Okay, and when we're talking about much larger, we're talking about something on the order of like 1,000 or much bigger. Does that make any sense at all, guys? We're not talking about exact values here. We're just looking at the general concept. Okay, so with that in mind, we jump back to this question here. Are the reactants or products favored at equilibrium? What that actually is saying, what this question is actually saying is, was a lot of reactant used up? Or was very little product made? Both kind of mean the same thing. Okay, if a lot of reactant was used up, then we say product was favored. If very little product was made, reactants are favored. Okay, so reactants are favored when K is much smaller than 1. Products are favored when K is much larger than 1. So it's really when K is much smaller than 1 or when K is much larger than 1 that we actually care. So what is our K value? Well, to begin with, this question is answered by the value of K. So you look at the equilibrium constant value, and that's what tells you whether or not product or reactant is favored. So is K a large number or a small number? Huh? I would say large. I don't even care what the decimal, what the numbers are in front of the 10. Times 10 to the 33rd. That's a pretty big number, okay? Something times 10 to an exponent of 23 is a little big. You could even go so far to say gigantic, enormous, okay? Is huge. This means what? Reactants are favored or products are favored? Products are favored, okay? This means products are favored. So those first two questions, if you understand delta H, if you understand the equilibrium constant, are actually really easy questions. Know your concepts, answer the questions very simply. Okay? Now, explain the effect on the equilibrium of the following. Before I get there, you guys okay with A and B? Okay. Because to explain C, we're going to talk about one more concept, but I want to make sure that A and B are okay. You guys feel comfortable with A and B? Or are there any questions you have about A and B? All right. So let's talk about Captain Obvious and his discovery of Le Chatelier's principle. I am a little bit of a jerk. I call Le Chatelier Captain Obvious because to me, this concept makes so much sense that I think it's obvious. Okay. Now, if it's not obvious to you guys, that's not a problem. It just means it's obvious to me. Okay. It just means it's obvious to me. So Le Chatelier's principle says essentially well, it literally says when stress is applied to a system at equilibrium, the equilibrium shifts to relieve the stress. If stress is placed upon a system at equilibrium, the equilibrium shifts to relieve that stress. Literally reading to you guys from my study guide, the word stress means anything that disturbs the original equilibrium. So once a reaction reaches equilibrium, things can happen that move it away from equilibrium. You can imagine an example of this would be even like taking a pendulum, taking an object that is a pendulum, letting it go, it'll swing back and forth, and eventually it'll stop because it reaches an equilibrium point that it likes. And that equilibrium point for the pendulum is pointing straight down, right? If you can imagine that in your head, then if I take that pendulum that's now pointing down and lift it up again, I'm disturbing it from its equilibrium. And it'll shift back and forth until it reaches its equilibrium point again. That makes sense? So the word stress means moves the reaction away from equilibrium, means something that moves the reaction away from equilibrium. Okay. If you move the reaction away from equilibrium, the reaction will shift in a direction so it heads back toward equilibrium. What that means with respect to the equilibrium constant and expression, the actual K value remains the same. So the value of K will remain the same at equilibrium. Once equilibrium is reached again, the K value will be the same. Okay. So the K value at the new equilibrium will be the same as the K value at the old equilibrium. That does not mean concentrations will be the same. That means the ratio calculated, the K value itself will be the same. Okay. The things that can affect equilibrium are as follows. Stresses for the reaction A so stresses placed on this system could include changes in concentration of A, concentration of B, concentration of D, or concentration of E. The changes in concentration of a reactant or product will alter the state. It will no longer be at equilibrium. If you add more of a reactant, if you add more of a product, or remove some of these. If you pull out of the container some of these things, that removes stuff from the container. And so it's no longer at equilibrium. The reaction will then speed up. Either the forward reaction will speed up or the reverse reaction will speed up, okay? If you add A, B, or remove D and E, the forward reaction speeds up temporarily to restore the K value. Okay. If you add and something to keep in mind is when you reach equilibrium, the rates are then again equal. At equilibrium, remember, the equilibrium means the forward reaction rate is equal to the reverse reaction rate. That's what equilibrium means. The rate of the forward reaction is equal to the rate of the reverse reaction. Okay? They temporarily are no longer equal when you either remove A or B, remove D or E, or add A and B. When you change the concentration of one of the things in the reaction, it's going to shift, speed up in one of those directions, okay? And an image to use in your head is the chair is sitting at equilibrium, right? The chair is sitting now at equilibrium. That is forward, this is reverse. Going that direction, you make product. Going this direction, you make reactant, okay? If I push on the chair in that direction, I've either added reactants or I've removed product, okay? If I push on it in that direction, I've added reactants, okay? If I'm standing on the opposite side, I'm going to remove product and I pull on the chair, it goes in that same direction. So removing product is the same type of stress as adding reactant. That makes sense? Okay. So if you add product, add D or E, or remove the reactants, A and B, the reverse is true, okay? Reverse reaction speeds up to, again, restore K, where now the forward reaction rate is now equal to the reverse rate again. Okay. I emphasize that because that is that fundamental condition required for equilibrium. The forward reaction rate must be equal to the reverse reaction rate to reach equilibrium in the first place. And if I remove A or B, that's like pulling the chair toward reactants. Okay. If I remove a reactant, I'm pulling the chair in the direction of the reactants. If I add D or E, that's like pushing of the chair in the direction of the reactants. Okay. Does that make sense, guys? Okay. Good so far. So that is what happens when you add or remove products or reactants. With me so far? Okay. From there, that's the effects of changing concentration. Temperature has an effect on reactions that are endothermic or exothermic. Okay. And think about it this way. Endothermic reactions have delta H as a reactant. So it becomes AA plus BB plus delta H be in equilibrium with DD plus EE. Now think about the whole previous explanation I just gave you. If delta H is a reactant, then adding heat to an endothermic reaction, adding heat will drive it toward product. Removing heat will drive it toward reactant. Okay, does that make sense? Exothermic are just the opposite. It's A plus B in equilibrium with DD plus EE plus delta H. Remember, exothermic means energy is released, so therefore it is now a product. So if you remove heat, pull on the heat, you're going to pull the reaction toward product. If you add heat, you're going to drive it toward reactant. Does that make sense? It's just a push and pull. That's the basic idea of this. Good so far. Okay. Pressure is a little bit more tricky. In general, change in pressure only affects a reaction if there is an entropy effect on the reaction. So if you have X plus Y in equilibrium with a single thing Z, increase in pressure favors the direction with fewer total number of molecules. So you have to count molecules including the coefficients. Okay, so if there were coefficients here, that would make a difference. Here, there's not. But an increase in pressure will favor the direction with more molecules. So if you increase the pressure, it'll favor reactants here. Okay, because the reactants has 2, products has 1. So increase in pressure will push the reaction toward reactant. Decrease in pressure will drive it, or sorry, increase in pressure favors the direction with fewer total. So increase in pressure favors product because it favors the side with fewer molecules. Increase in pressure drives it toward product. Okay, that should make more sense actually. Increase in pressure toward product. 2 becomes 1. Okay. Decrease in pressure favors reactant. Decrease in pressure will favor things with more molecules, so it'll go toward the left side. Decrease in pressure. Okay. And how do you increase or decrease pressure? Well, one way you do that is literally taking a container and squeezing it down to a smaller size is how you increase the pressure, and you decrease the pressure by expanding. Okay. So it makes sense that if you have 2 things, they're going to be happier when you start squeezing to be 1 thing. If you expand that, it's perfectly fine for there to be that 1 thing become 2 things. It's perfectly fine. There's nothing preventing it. It'll go in that direction. Okay. Does that make sense, guys? Okay. This is entropy driven. Good so far? Okay. Final thing then. Catalysts. What does a catalyst do? Does anyone know what a catalyst is? A catalyst speeds up rate of reaction. Okay. Catalyst speeds up rate of reaction. Good so far? For reversible reactions, catalysts for reversible reactions. Write this in a more, I'm going to write the same words. I'm just going to make it more clear. For reversible reactions, catalysts speed up both forward and reverse reactions equally. Therefore, catalysts do not affect equilibrium. Catalysts have no effect on equilibrium because they speed up both reactions equally. All a catalyst does is lowers the energy of activation. The energy of activation, well, lowers the energy of activation for forward and reverse equally. Okay. You guys okay with that? Catalyst means no difference on the equilibrium. Okay. That's all you need to truly immediately understand is catalysts don't affect equilibrium. Okay. Any questions? Okay. Then we'll jump back to this question. Increasing pressure by decreasing volume. If you increase the pressure on this reaction, so increasing the pressure on this reaction do this with me. We've got what's the reaction? The reaction is Cl2H2 2HCl. So that's our reaction. Cl2 plus H2 giving you 2HCl. Increase the pressure by decreasing volume. Is there an actual difference in the number of molecules on the reactant side versus product side? How many do we have on the reactant side? 2 molecules. Products? The products is 2 molecules. Okay, there's a 2 in front of that HCl. That means 2 HCl's are there. So no difference in number of molecules. Pressure change has no effect. Okay, because 2 and 2 are the same. There's no difference. There's no effect. Good so far? 2. What's number 2? Number 2 is increase the concentration of HCl. So if you increase the concentration of HCl, which direction is the reaction going to go? It's going to go toward product or reactant? If you increase HCl. Have you added product or added reactant? Is that a product or reactant? You're adding product. So that's going to be pushing it directly toward product or pushing it toward reactant. You're now pushing, okay? And when you've added, means pushing, you are pushing toward reactant, therefore favors reactant, okay? When you add something, you push it in the opposite direction. If you add product, you push it toward reactant. If you add reactant, you push it toward product. That's something to keep in mind. Adding means pushing away from what you added. It's like a tug of war. In a tug of war, if you push on the rope, are you going to win the tug of war? No, you're going to lose, right? So if you push on the rope, you're going to push it toward the other direction. So think of a tug of war there, okay? Adding means pushing in the direction away from yourself. You're not pulling, you're pushing. In a tug of war, you're pushing it towards your opponent. You're pushing it away from yourself. Decreasing the concentration of Cl2. So decreasing the concentration, decreasing or removing means, does that mean pulling or pushing? It means pulling. Okay. When you decrease or remove something, you're pulling on the reaction. Okay. Another way, I mean, there are some weird analogies I'll come up with for this, but for this one, imagine a tree and you're trying to add or remove things from the actual tree itself, okay? Imagine like a tree and you cut into the tree on this side. If you cut into it, it's going to go in that direction, okay? You're pulling towards yourself is the same thing with the tug of war. If you are removing something, you are pulling toward yourself, okay? That means pulling. So removing a reactant favors reactants. Okay? Does that make sense? Okay. Number 4 is increasing H2. Increasing H2, adding H2 is pushing on the reaction. So therefore, you're going to push it in the direction of product. Does that make sense? And finally, adding a catalyst does absolutely nothing. Adding a catalyst does absolutely nothing. Question. Because a catalyst increases the speeds of the reaction, both forward and reverse, equally. I want to emphasize that one finally here. 5. Catalysts increase reaction rate by lowering the energy of the transition state. And this will bring me directly to one of the last things I want to say about this problem. When we looked earlier at delta H versus time, and you looked at A versus B, and we had a reaction progression energetically like this, and this right here, this is our transition state. And there's a whole lot of things here. Energy of the activation energy for A is this right here. The energy of activation for B is this right here. But when you lower the transition state, both of those energies of activation change equally. Okay. So the moral of the story is catalysts have no effect on equilibrium. You have a question? This applies to all catalysts, all questions regarding equilibrium. This is not just, so everything I'm saying about pushing, pulling, catalysts, pressure, these all apply as general rules with regard to equilibrium, not just this question. Yeah. So catalyst effect forward and reverse reaction rates equally. And of course, the moral of the story means no effect on equilibrium. Okay. So, yes. You got 65 now? Okay. Then let me just very quickly go. That was 60. Let's glance at 65 if I can even find it. Maybe I didn't even get to it. Oh, there it is. Okay, so 65. I2 added, H2 added, a catalyst is added, temperature is increased. Okay? That is exactly like 60. You're absolutely right. The only difference being you need to look at H2 plus I2 in equilibrium with 2HI and take into consideration this delta H and what it means for it to be a negative value. Okay. Now, before we go, I asked last time, any other questions with regard to material, any concerns you guys have, look briefly at the assignment I handed you. Look briefly through limiting reagent worksheet. Does everyone have a copy of the limiting reagent worksheet? Does everyone have a copy of the limiting reagent worksheet? Question. Oh, no, you need a copy. Anyone need a copy of the limiting reagent worksheet? Or does anyone know someone who's not here today that would still benefit from getting a copy from you? Okay. This is due in 1 week, the day of the exam. The exam is next week. Study, study, study. Ask questions. Send me emails. Please email me if you have questions. Questions. I will definitely upload this. Yes. Okay. This will be uploaded. All the previous videos will be uploaded. We'll be good to go.